Have you ever wondered why fractions were invented? Or whoever thought it was a great idea to put a negative in front of a number? Today we are going to take a look at why some of those weird numbers exist and why anybody would come up with them. Thank you for stopping by here at Tao2Pi. I am Caesar the Tutor, and today we are going to be taking a look at the sets of numbers. The natural numbers, the whole numbers, the integers, the rationals, the irrationals, and finally, the real numbers. First, let's talk about a set. If you look at the clothes you're wearing, that would make the set of clothes that you are wearing. If you look at the clothes in your wardrobe, as in all the clothes that you own, that will be all the clothes, including the set of clothes you're wearing. Another way to look at it is that the furniture in this apartment belongs to the set of furniture in the apartment. If I were to buy another couch, then I would be adding more members to that set. If I were to buy a computer and bring it to the apartment, it would not belong to the set of furniture. However, we could extend the set and say that now it belongs to the set of stuff in this apartment. And now the set of furniture plus the computer belong to the set of stuff. Of course, this being an algebra class, we're not going to be working with sets of furniture, but we are going to be working with sets of numbers. And numbers can go on forever, or they can stop if we limit them in some way. In the beginning, before we invented the current number system that we use today, it only made sense to count things as we saw them. One marker, two markers, one cow, two cows, one stone, two stones, three stones, four stones. And we knew that we can keep going and going and going forever until but we now know that we can start counting at 1 and continue 2 and 3 and that we're never going to finish. So we use these three dots to say that we can keep going forever. We call this set the natural numbers. And the numbers are natural because it's natural to us to count. We never start counting from 0. We don't say, I'm going to count my money. 0, 1, 2, 3. We don't do that. Naturally, we start with 1. So we're going to call these the natural numbers. And in books, it's going to have some curly notation for an N. On the board, teachers tend to write it as a capital N with an extra stick attached to it right there. So it looks like it's a little thicker. And this will be the set of natural numbers. And the set of natural numbers is nice because we can take any natural number that's in here, we can add two natural numbers, and we know we're always going to get another natural number. And you can try it. As long as you limit yourself to from 1 all the way to infinity, you know that as long as you add two of those numbers, you're going to get another number in here. Another nice thing about the natural numbers is that we can multiply them. We can multiply two of those numbers, and no matter how many times we try, every answer is also going to be inside the natural numbers. But of course, at some point, somebody realized that we had to account for nothing when we write it down. How do we symbolize the fact that we have nothing? And the 0 was invented. And then, of course, somebody decided to subtract, and that completely broke us down because we could subtract numbers like 5 minus 3, and that's 2. That is completely fine. 2 is in the natural numbers, which also happens to be in the whole numbers. But if we reverse this and say, well, what does 3 take away 5? If we only have to choose from these numbers, we don't have an answer. We have no solution. Let's invent a way to symbolize numbers that went in the other direction. And a lot of times, a lot of students get confused about what a negative means. And a negative simply means in the opposite direction. Okay, so that's all you have to think about. In real life, when somebody says negative, people think bad. But in math, it simply means go the opposite way. We know there's going to be negative 2. And so we had to include the negative 2 somewhere, but we cannot include in the natural numbers because it's not natural to count negative 2. And we cannot include in the whole numbers because the whole numbers have to be positive and whole. So then we extended it to another set that we're going to call the integers. And now the integers include all these numbers here plus all the negatives of the natural numbers. So now we're going to have a negative 1 to play with, a negative 2, a negative 3, and all the other negative numbers. In a number line, it looks like this. We now have 0. We also have 1. We also have 2. We also have 3. And based on the fact that now we invented this negative, we are allowed to not only walk in that direction, I'm allowed to walk in that direction as well. So now I'm allowed to go to -1, -2, and -3. But this number line is actually not complete yet because our values here, the whole numbers, the naturals, and the whole numbers do not include any numbers between -3 and -2, -1 and -2, 0 and 1, -1, or any of these numbers. It's not a number line yet. It's simply coordinates because we don't have fractions in here. We cannot divide. If we say what is 4 divided by 2, that's fine. That gives us a 2. 2 is a natural number. That's okay. But if we reverse this and say, well, what is 2 divided by 4? And we know that we can rewrite this as 2 divided by 4. And if we reduce, we get 1/2, but 1/2 is not a natural number. It's not a whole number, and it's not an integer. So now we have to extend our set again. Now the integers are symbolized by a z with a double line as well. In this new set that we're going to extend, that includes my numbers like this, remember that this, another word for fraction is ratio. So this is going to be the set of rational numbers. And for some reason, they use a Q. I think it means quotient, as in division. I don't know. Now this 1/2 is going to be included in this set. And so now we're slowly filling in all the points in between this number line. But we're still missing a few numbers. And these rational numbers are going to be all the fractions. So these rational numbers are going to be all the fractions, all the numbers that can be written in the form a over b. So that just means any number that can be written as a fraction, such that b cannot be 0. So the definition of the rational set says that b cannot be 0, and so these two numbers could be anything that are from these other sets. Of course, we're not completely done yet. There is another set that we're going to talk about, which includes all of these plus another set of numbers that fills in all the gaps. And these numbers are the irrational numbers. Now, the irrational numbers combined with all these numbers are called the real numbers. And that's what we call the real number set. Irrational numbers are numbers such as pi, e, and other numbers like that that cannot be written as a fraction, or even numbers like square root of 5, square root of 2. Any square root that does not simplify to a perfect square is going to be an irrational number. And if we did not include them in here, we would not be able to solve problems such as circumference of a circle because it includes pi. We would also not be able to solve functions such as x squared equals 2 because we would not be able to take the square root of both sides because this number is irrational. So that extension allows us to do the majority of operations that you will be needing for Algebra 1. Now there is another set that includes all this, and of course there's more sets, but there's another set that includes this. It's called the complex, and we're not going to go into that here. That's when you start getting into imaginary numbers and all that other stuff, but we're not going to get into that in this video. Now let's take a look at this diagram and see how we can put everything together. The natural numbers, as you can see, it's this innermost set, and then we extended it to the whole numbers. So that means that all natural numbers are whole numbers. And then we extended that one to the integers. So that means that all whole numbers are integers. And then we extended that one to the rationals. And the rationals include all the integers, all the whole numbers, and all the natural numbers. But then outside of the rationals, we have the irrationals. This includes all the numbers like pi, e, square root of 2, square root of 5, all the non-perfect square roots. And if we take these two sets together, we get the real numbers. So let's take a number like 1/2. 1/2, because it's a fraction, it's going to be a rational. Now, because it's a rational, it's out here, so it's not any of these. And because it's here, it's also not irrational. So it's a rational, But it is a rational and a real number. So we say this is rational and it's also a real number. Let's take a look at negative 3. Well, negative 3, since it's negative, we know it is not a natural and we know it's not a whole number, so it already belongs to the integers. Because it belongs to the integers, it also belongs to the rationals. And because it belongs to the rationals, it also belongs to the reals. So in this case, we're going to say integer, rational, and real. Well, pi, we already know pi is irrational. So it's not any of those. So we're going to say it's irrational. And it's real. That is all for today's lesson. Thank you for stopping by. If you like the video, make sure to hit the like button. If you want to see more content like this, make sure to hit the subscribe button. And if you have any questions, comments, concerns, or emotional outbursts, make sure to put them in the comments below. Thank you.